Well, hello everybody, Dave here, and this is the second in a series of lessons on describing relationships using two quantitative variables. In the previous lesson, we started talking about what a scatter plot was, and some of the basic understandings of how to describe them, and more importantly, what one of the particular calculations known as the correlation coefficient is that we could actually do and what it told us moving forward. So our understanding of FODs and the quantities that are described by that relationship are going to be super helpful here when we start talking about now how we actually find a way to describe trends that we have identified using what's known as regression lines. So let's start off with a scatter plot relating the price of a vehicle in dollars versus the number of miles that it's been driven. We can see from the scatter plot itself that we could represent this according to a linear form, and we could talk about this as being a negative association because, of course, we can see that there's somewhat of a negative slope associated with this form as it moves from left to right. But now what we will do is we'll actually fit a regression line to try and represent this relationship that we believe we are seeing. Now, regression line by definition is just trying to describe this response variable relationship to the explanatory variable, and it doesn't necessarily have to be a line, but for the case of this course, it will be a line. If you notice on your TI calculator, you have other regressions that you can use, and sure enough, if you have a curved relationship or some sort of exotic relationship that you want to fit, you will actually have ways to do that. But for the sake of this course, we're going to stick to fitting a regression line to a scatter plot that we have already deemed to be a linear form in nature. Now, when we come up with a linear regression equation, it's important to remember that we already know something about how to create linear equations. Way back in Math 8 or sooner, you found out that y was equal to mx plus b, where m was the slope and b was the y-intercept. Well, that's not so different from statistics except for the way that the notations are. The first thing you have to recognize by the regression line is its y hat is equal to a plus bx. Well, why is it in the order of a plus bx instead of bx plus a? And the answer is, if we wanted to now add a second or third or fourth variable to this particular relationship, we would simply add it to the end. It's a common convention for statistics to go with the constant first plus the slope times the first variable. If we had a variable, say z, we would add c times z to the end, and so on and so forth. But this y hat is very important because the hat represents that it is a predicted value for the response variable y. This means that anytime you see a hat over a variable, you know that it's a predicted value, not an actual observed value. This will be important later on. As we know from previous exposure, b is now going to be equal to the slope as it's attached to the explanatory variable x, and a is going to be our y-intercept when x is equal to 0. Now, I encourage you strongly that as you go through this unit and as you work with regression lines, I would very much avoid the use of y's and x's now. That is very much a pre-calculus and regular math type scenario. Here in statistics, we want everything to have meaning, and so because of that, y's and x's may not be the most descriptive variables used. That being said, if you do use those, please use let statements like you used to when you first started doing algebra to tell us exactly what those particular variables mean. So for example, let y hat equal the predicted value of the car, for example. Now, if we have the regression equation like I've shown you at the top here, there's a couple of things I want you to notice. You'll notice that I've avoided the whole y and x thing simply by labeling them according to the axes given. So price hat is equal to 38,257 minus 0.1629 times the miles driven. This is going to be the type of regression equation that you're going to see most often in statistics. And don't be afraid to write out statements like that as miles driven or as price. It is very descriptive and it is very attached to the relationship that you see in your scatter plot. So now we get into the scripting of what we're looking at here. And the first thing we'll do is we'll actually identify what the slope is and interpret it in the context of the question. It's important to recognize that anytime they say interpret, you are always referring to what the value actually means and how it relates to the context of the problem itself. So in this case, the slope is going to be that negative 0.1629 value, and it tells us the price of a used Ford F-150 is predicted to go down by $0.1629 for each additional mile that the truck has been driven. It's important to recognize that we aren't simply just stating what the slope is, but we are saying that for every individual unit in the horizontal direction, the value in the vertical direction is either going up or down depending upon what kind of relationship you see. Now, how did we get this regression equation? We simply used our TI calculator or any sort of graphing calculator you have, and you do the linreg in brackets a plus bx. You put your data into your calculator in lists, and you're able to crank it out pretty quick. I would encourage you strongly to either Google how to use that technology or go into a textbook if you have it. Certainly, my class's textbook has a very nice textbook that has a section dealing with the technology use. If we want to talk about the y-intercept now, remember that in statistics, if it has meaning, we should go ahead and state it. And in this case, the meaning of this y-intercept is the predicted price for this car when it has 0 miles driven, i.e. it is brand new. And so this would be very useful to car lots or car manufacturers that are trying to come up with prices of the cars, just simply based upon the market and how far they drive and how much they're selling for. So this is very much a realistic interpretation of what you would do with a scatter plot like this. So let's go ahead and use our linear regression now to predict what a certain value is going to be. And let's say we want to know how much the car could sell for when 100,000 miles has been driven on it. We have our regression equation to start with, and it's important that whenever you do a question like this, you always start by stating your regression equation. If the equation isn't given, well, obviously you have to find that first. But once you have it, make sure you state it before you substitute any values in so that anybody who's looking at it understands that you at least knew that that was the equation to use. Now we can substitute in our 100,000 miles to show that this is the value of miles driven that we're trying to predict the price for, and we get our predicted price of $21,967. Now, does this mean that the car will actually sell for this much? And the answer is maybe, maybe not. It is the predicted value based upon the trend associated with the sales of all of these Ford F-150s and their respective miles driven, and based upon that trend, we believe that a fair predicted price for this value is $21,967. Now, you'll notice that when we predicted, we stuck within the domain of our data. And so we're in between the points, and we're not trying to predict somewhere outside of these points. For example, if we wanted to take a look at something like 400,000 miles, well, we don't have data to represent that, and because of that, the prediction that we have for that value may not be as accurate as what we have now, based upon the fact it's in between the observed data, and so we know that we have a reason to believe that this trend is effective to predict the value at that point. To predict the value outside of this is considered extrapolation, and in statistics it's a big no-no. What we just did on the previous slide is known as interpolation because it is inside the domain of our data. But if we're trying to extrapolate and talk about things outside of our data, it is a big no-no because we aren't 100% certain or even certain at all that that trend is going to continue. For example, with the truck discussion, there will be a certain point where a certain miles driven ends up with a value of 0, and beyond that ends up being a negative value, which would imply that you have to pay money even to drive it. Well, that doesn't make much sense, and a car being worth 0 doesn't make much sense either because you certainly have the value in parts and things of that nature that you could always sell it for. So extrapolation is a risky business, and we typically try to stay within our domain. And if you are going to extrapolate, do so very sparingly, i.e. not very far outside of your data. I would stick very close because it is reasonable to assume that maybe a little bit outside it might be predicted, but otherwise don't do so. An example I use in class would be something like your weight over time starting from birth. When you are born, you are weighing a certain amount, and you certainly grow quickly. And if you extrapolated that relationship into your 40s, 50s, 60s, or beyond, you might weigh as much as 3-4 tons. So it certainly wouldn't make sense to extrapolate there because the trend changes. Please don't think that every trend always will continue along its path simply because we've predicted it with a regression line. So one of the things you've probably noticed with the regression line is that most points, if not all points, aren't even on the line itself. You may recall from junior sciences in your education where your junior science teachers told you to wiggle the ruler around until you had about the same number of points above or below the ruler. At that point, we called that a best fit line. And little did you know, those junior science teachers were actually getting you to do a statistical calculation based upon this concept known as residuals. And the whole idea about a regression line is we are trying to make it a true best fit. But in order to do so, we have to make sure that we minimize the value of what this is here, the residual, which is the vertical distance away from the predicted value. And so when you think about what you did back in the day with the wiggling the ruler, that's exactly what you're doing statistically, is you'd wiggle this slope up or down a little bit to minimize those residuals so that you know for a fact that it could not be a better fit than what it was. This is why we called it a best fit line. So residual is just simply the difference between the observed value and the response variable and the predicted value by the regression line itself. And so this equation here is really a very straightforward equation, but it's certainly nothing that's ever given on an equation sheet. So please remember that it's always observed minus predicted. Now, what do we do with residuals? Well, the least squared regression line, or LSRL, is it in fact minimizing this residual, and here's how it basically works. If we take a look at our original regression dealing with the price of the truck as a function of miles driven, what we did originally with a calculator is we allowed the calculator to take the slope of the best fit line or regression line and wiggle it up or down until it had a certain fit. Then it calculated the residual of every single point, and more importantly, it found the area, the actual residual squared. And so you'll see in the picture on the right, the residuals now are all being squared, and I'm representing that by areas. And what a least squares regression line does is minimize this sum of these squared residuals area. When that's done, you know you have a statistical best fit. So a least squares regression line is not simply just a guess or an estimate. It is a statistically calculated minimization of the area of the squared residuals. It's a fantastic thing, and you could imagine trying to do that by hand with a data set of any size. That would be quite challenging. So it would seem that residuals then provide us with an opportunity to have evidence to support that a particular regression or a particular relationship is indeed linear. And so for that, we could actually go to a residual plot. Now you'll notice again, the picture on the left is the original scatter plot that we've had, and you'll see that we have the regression line fit. Well, if we calculated each individual residual and then plotted that with miles driven on the horizontal axis, what you see is the picture on the right. And you'll notice that there's no form to the residual plot, that it essentially looks like randomized scattering above and below the horizontal axis at 0, representing that it would be an exact prediction where the observation was exact to the predicted value. Well, the fact that we don't see any sort of form to it, and the fact that it apparently looks random, this is the definition of what would represent evidence to support that this regression fit to the linear form is indeed a good fit. And the reason for that is if it wasn't a good fit, if maybe it was curved data, we would see more of a form or a consistent deviation away from our predicted trend, and that would suggest to us that perhaps there was another form present. And so this is a really good piece of evidence when you are asked to determine whether it is appropriate to use a linear regression for your data set. I've come across many graphing examples where students simply throw a trend line on something just because a computer does it for them, and they don't stop to think if that's appropriate to do so. The residual plot is the answer to the piece of evidence you need to justify that fit. So if we had some data that was not linear in nature, let's say the graph on the right, which is a classic quadratic function, you can see that the graph on the right is obviously curved, and if for whatever reason we decided to try and fit a trend line to that, you can see that a trend line certainly gets fit, and again, that is statistically calculated such that it minimizes the square of the residuals and the sum of that area. But you can tell that if we look on the left where the residual plot actually is, you can see that the residual plot has a very systematic deviation away from this linear trend. And the fact that we see this picture, the fact that we see this curve to the residual plot, indicates that it is not appropriate to fit a linear regression line to this particular data set. There would be some other relationship we'd have to consider. And again, within the realms of AP statistics, we only focus on whether things are going to be fit by linear trends or not. We're not going to go through the process of fitting it with an appropriate power trend or something to that regard, which would be more appropriate to this data set. So if you see a pattern within the residual plot, then you absolutely state that it is inappropriate to use a linear regression for that particular data set. Now, it would make sense that if we were talking about prediction and prediction errors, that residuals would have a standard deviation associated with it, or the typical prediction error. For that, we get the standard deviation of the residuals, or lowercase s. You can see with the equation that we have the sum of the residuals squared, which is exactly what we did to calculate the least squared regression line. But in this case, we have a value of n minus 2. And if you remember way back when we first started talking about standard deviation, we had n minus 1 to represent the necessity of 2 points to actually have a standard deviation. Well, in this case, if we have a linear regression and we need to find the standard deviation of the residuals, the first 2 points would represent the points that create the line. The third point is going to be the point that now will result in some sort of measurement residual. So the n minus 2, as it was with regular standard deviation, means that we require 3 points for there to be a standard deviation of the residuals at all with a scatter plot and a least squared regression line. So again, we're talking about the approximate size of a typical prediction error. The other quantity which is really important when it comes to how good your fit is the coefficient of determination, or r squared. And as I said in the previous lesson, when we were dealing with the correlation coefficient, a lot of people use r squared as a correlation description, but in actual fact, what it is it's representing how good of a fit your least squared regression line actually is. And so if you see by the equation here, it's this big ugly equation dealing with the average of the y values and the squares of the residuals and the sum and things like that, but there is going to be no mechanic where you actually have to calculate this by hand. Your graphing calculators will do this for you, and if you know how to calculate the correlation coefficient, wouldn't you know it, r squared truly means r squared, and so you would simply take the correlation coefficient and square it. Conversely, if you wanted to find the correlation coefficient from the coefficient of determination, you could simply square root it. But it's important to recognize that, again, a better way to think about the r squared value is that it is actually trying to tell you how good of a fit it is, how well does it actually predict the variations in your data. So let's go back to an example that we had in the previous section dealing with the college football leagues and the number of wins as a function of points per game. We now have a least squared regression line fit to it that shows us the slope and the y-intercept, and we now also have the residual plot, the standard deviation of the residuals, and the coefficient of determination r squared. We are now taking a look at all the tools that you have to appropriately describe and analyze any two quantitative variable system where we have a scatter plot scenario. Well, you can see here just by looking at this before we get into the question itself that we have a residual plot that is essentially random, which represents the fact that our form is indeed linear, as there is no sort of identified pattern within the residual plot. The r squared value is a fairly high value, which tells us that it's a fairly good predictor of the actual data set itself. And the s value, or the standard deviation of the residuals value of 1.24, tells us that it is typically off by at least one win, which again is a pretty good predictor by itself. Again, I will say that although this particular question shows y hat and x, I would encourage you not to use y and x when you are writing out your regression lines in the future. So let's go ahead and do some questions to show you how this looks. Calculate and interpret the residual of South Carolina, which scored 30.1 points per game and had 11 wins. So again, we start very simply with the least squared regression line, because in order to calculate the residual, we have the observed value, but we need the predicted value. I show in my class a way to use your calculator to go from the beginnings of data in order to calculate both the residuals based upon calculating the predicted values very much recursively so that you don't have to calculate each one individually. So definitely go learn that technology. It's going to help you along. But you can see here that the predicted value is 9.4 wins. When we are calculating the residual and the predicted value is some weird non-real answer like 9.4, there's not going to be 9.4 wins. It's going to be either 9 or 10. You leave it as a decimal value because, again, the residual is relating the observed value and the difference of that from the actual predicted value. And in this case, we get a value of 1.60 wins. Notice in both cases we have units, just like we did with standard deviation and means and things like that. Make sure that you have the units to represent it as well. But you can see here that South Carolina won 1.60 more games than expected based upon the number of points they scored per game. So there's a couple of things here that are very important. The first thing is representing the fact that we are referring to this as the observed value is more than the predicted value. So this would be a case of underestimating the number of wins. The predicted value was 9.4, but the actual value was 11. So it underpredicted the number of wins that South Carolina was going to get. The second thing is when you're describing your residual, make sure you represent it that it is based upon whatever your horizontal or your explanatory variable actually is. Don't just simply say they won 1.6 more games. Definitely put some context to it, or else you won't really have demonstrated that you understood how it connected to the whole question. If we go through a sampling of more questions now, is the linear model appropriate for these data? When you see this question, and see it you shall, it is a simple question where you make a residual plot. You simply make a residual plot, sketch it out on your sheet or wherever you're writing it down, and then describe whether you see a pattern left over or not. In this case, there is no pattern when we calculate the residual plot, therefore a linear model is appropriate. Simply stating the r-squared value or the r value is not going to be evidence to suggest that it is an appropriate linear model, as I will show you at the end of this lesson. If we want to interpret now the standard deviation of the residuals at 1.24, again, we put it in context and we show that the least squared regression line where x were the points per game and the predicted values of y were the number of wins, we will typically be off by about 1.24 wins. You can hear the wishy-washy language of this all over the place. We will typically be off by about 1.24 wins. And again, that is the average or the typical deviation away based upon the residual count. The final one, which is a very scripted answer, is interpret the value r squared is equal to 0.88. I would encourage you strongly to simply write something like this out where you give yourself blanks to represent where you would fill in the context of the problem. But about 88% of the variation in wins is accounted for by the linear model relating wins to points per game. So there's so much loaded here in this answer. The first thing is representing the r squared value as a percentage. The second thing is representing the fact that it is talking about the variation in wins accounted for by the linear model. It's not saying percentage of data. It's saying the percentage of the variation in wins accounted for by the linear model relating wins to points per game. Now I've put the context of what linear model I'm using. That, my friends, is a very scripted answer for what the coefficient of determination is. And whenever you're asked for something like that, you absolutely need to include all of that information. The fact it's variation in the quantities, the fact that it's a percentage, and give me the context of what the linear regression actually is. There are some final things that I want to talk about in this unit that I think are very important. The first is understanding that if all we had to do was create scatterplot after scatterplot after scatterplot, that would be a lot of work and it would take a lot of time. And that doesn't make sense for me or anybody like me to do that to you every single time. So instead, you can expect the fact that you're going to have computer printouts. And here's an example of a computer printout, and from it you just have to be able to understand that the first value, or the constant value, is our y-intercept. Our second value is our slope. We have our S value. Now notice that this is the standard deviation of the residuals, even though it has a capital S. That's annoying, but it's a real thing with these computer printouts. Just interpret it appropriately. And then we have the r squared value. Instead of the adjusted r squared value, it's simply a different algorithm used to calculate that, which we don't teach in AP statistics, so simply use the r-squared value of 66.4 in this case. It's important that from all of these tables that you can glean out the slope, the y-intercept, and the value of s and r squared. Here's another printout that gives you very much the same information. You'll notice again that it's actually split up into a summary of fit as well as the parameter estimates. It's important just to be able to look at this. This is a JMP printout. The other one was a Minitab printout. And so again, just those titles of Minitab and JMP are certainly worth remembering for the sake of the AP statistics questions moving forward. There is a way that you can find the least squared regression line without having the data at all. And it's if you have the standard deviations of the explanatory variables and response variables, as well as the average of the explanatory variable and the response variable. And these equations here, b is equal to r times sy over sx, and a is equal to y bar minus b times x bar, are the two equations you can use to find the slope and the y-intercept of your regression line. Something nice that you see that's built into this question is the fact that when you have the slope, you need one more point to find the y-intercept. And one of the truths of the regression lines is that the averages of the horizontal and vertical data, specifically x and y, are on that line, x bar, comma, y bar. So that's a great thing to know. If you can figure out a way to find the slope, you definitely have a point if you have the data and you can find the averages of the x values and the y values. So there are scenarios where you may have to use this, but those scenarios will only be if they specifically state these quantities of the data without giving the data itself. Otherwise, you would definitely want to go and use the data and calculate it as we have before using a linreg of some kind. There is some wisdom associated with dealing with regressions and correlations and scatter plots in general. And the first thing I want to recognize for you is the importance of the distinction between the explanatory and response variables. It's important that you understand that in any given study, there is going to be something that the people are controlling and what they expect to change as a result of what they're controlling. That's why it's literally called the explanatory variable and the response variable, which responds to the explanatory variable. And so you can see two plots down here where it's the price versus the miles driven, and then we flip it and say the miles driven versus the price. It's exactly the same scenario that we talked about with the Ford F-150 and the trucks, and what you can see is that the regression line equations drastically change, and so does the standard deviation of the residuals, but you'll notice that the coefficient of determination, r squared, doesn't change at all, and that's just based upon the mechanics of how it's calculated to begin with. And so r squared as a piece of evidence to suggest that you've done the right plot won't be effective for you because it would be right regardless of if you did y versus x or x versus y. So be very careful because in statistics, even though mathematically you would get the same answers with a little bit of algebraic manipulation, from a understanding standpoint, you haven't demonstrated that you understood which variable was which, and that's going to cost you. So be very careful with the way that you plot. The second thing is that correlation is really not going to be a good measure of whether something is linear or not. And I give you 4 plots here, and you can see 4 drastically different plots, yet all of them have the same linear regression equation and the same correlation coefficient. And what that means is that correlation is not itself a way to determine whether something is linear. At the same time, a correlation coefficient is only used to describe linear relationships. So again, it's not a proof of something being linear, but it is only used in the case of something being linear, because we're talking about the strength of the linear form that we see. For those of you that are looking at the other 3 plots and wondering how those end up with the same lines, you have to remember that outliers or extreme values in a scatter plot will drastically affect the slope. And so even though most students want a line to simply follow all the points in C and just ignore that particular point that is far above at about 12,13, it will actually be driven up higher away from the points again, to minimize the areas associated with the square residuals. So now that you know something about the mechanics of how a regression line is made, you know that there's no way that you simply ignore the data. The same thing is true for D, that most people want to just draw a vertical line and ignore that point way out at 18, call it 13. But really that point out there is driving the regression line in that direction itself, and the residuals of the points in the vertical there will all be minimized by the line going right through the middle. So again, even though it looks like we should just ignore points, in the case of statistics, unless there is reason that we can eliminate it, besides the fact it doesn't look good to our data set, then you have to include it when you do the calculated regression lines. The last thing that's really important is to recognize that correlation and regression lines are not resistant to outliers. And so if we take a look at these three regression lines here, we're focusing on 2 points. We're focusing on the point that's labeled as child 18 and the point that's labeled as child 19. And you can see on the right-hand side there that we have the results of our calculation of the correlation coefficient and the regression lines themselves. And you can see that when we remove child 19 but leave child 18, that we still have a regression line that's similar, but our correlation has improved because we've removed a point that has a substantial residual. However, if you remove child 18, you're drastically affecting the way that the regression is going to be directed, because that point is very much driving those regressions down and to the right. And the result, as you can see, is a vastly different regression line and correlation coefficient. And so it's important to recognize that one point, it doesn't take a lot of points, simply one extreme point or one point that is important to describing the overall trend. When that is removed, it can drastically change what your regression line and correlation look like. So that brings us to our last definitions that are important to us when describing this idea of correlation and regression lines and points that matter significantly. We've been defining an outlier throughout this unit as a value that has a significant Y residual, that it is very much high above our regression line or our predicted values. At the same time, we don't talk about it in terms of the horizontal value, because it's the residual that really makes it considered an outlier. At the same time, if you have a point that is very far along your domain, along the explanatory or the horizontal value, then that value can be significantly influential in the statistical calculations associated with our linear regression. If you think back to the charts that we just looked at, the child 19 point is certainly an outlier, but the child 18 point is influential because it drastically changed the results of the statistical calculations. So it's important to recognize that outliers are not necessarily as influential as a value that is far along the horizontal axis that is helping to direct that linear regression line. So there is certainly a better answer to whether something is influential or not than just simply saying that it is an outlier, because something horizontally along the domain is not necessarily considered an outlier if its distance away from our regression line is not a significant residual itself. So that's it for this set of lessons on describing relationships involving two quantitative variables. We've gone over a bunch of different tools that you now have to successfully analyze any two quantitative variable scenario where we can understand the relationship better, and hopefully we can understand to what level we can predict and not predict certain values, and what can influence our overall results that may have hindered the study or perhaps given us a new direction for that study. So best of luck to you with all of your practice problems and things that you do with this unit, and we'll see you again.